Alright, so we've already worked through the example where we fit a line to a set of data. Now we're going to work through the example, a constant when we fit a constant, and now we're going to fit a linear line, right? So you guys may remember um, from your math class the equation of a line: y equals mx plus b, right? Well, we're going to end up generalizing this later, and so instead of y equals mx plus b, we're gonna represent it as y equals a naught plus plus a1x. You should be able to see a naught is b, m is okay. So you see it's the exact same thing. And I'll just note while we're at it that remember what we just did is y equals a naught. That was our constant. Y is just equal to a constant. Now all we've done here is we've just added on one term with another constant multiplied by an x. Okay, so that's all we've done here, and now we're going to go through all the same motions we did before. Alright, so we're going to try to find several things. So the one thing we're going to find is we want to find what is EI, right? What's our error? And that's just going to be defined the same way. That's the distance between the equation that we fit. Now we haven't fit this equation yet. We're going to derive the equations to get this from our statistics, but in the same way we've got this EI, that's the error, that's the distance between this line y equals a naught plus a1x, this line right here, and our point. Okay, so that's our error. And the other thing that we know is we're going to want to find our standard deviation. Now, standard deviation before we called SY, and instead of calling it SY this time, we're going to call it SYX. And the reason we're doing this is because it's not just a standard deviation. It's a standard deviation of this regression line because it's linear now, and so we just give it a slightly different name. But like before, that's going to equal the square root of the error, the sum of the error squared, EI squared, divided by, and that's from I equals 1 to n, divided by our degrees of freedom. And in this case, we're estimating two parameters. And so let's just see here. This is estimated, and this is estimated. Both of these coefficients we want to know. Before we only needed to know the coefficient a naught. We called it mu, but before we only needed to know the coefficient a naught. Now we need to know the coefficient a naught and also the coefficient a1. And so we're estimating two parameters. So the degrees of freedom then in this case is going to equal n minus 2. Alright, so degrees of freedom is going to equal n minus 2. That's great. Okay, so we've got some of our statistics, and now we actually need to figure out what this line is. Alright, well, let's just look at that then. So, here we go. Now we can just write out these equations. So we want to know a naught and a1, so we can write out these equations. So we go a naught plus a1 x1 equals y1. A naught, same a naught, plus a1 x2 equals y2. A naught plus a1 x3 equals y3. A naught plus a1, and so this goes right on down. So let's let's just put our little dots in here. Dot 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 a and a naught plus a1 xn equals yn. Okay, where n is some huge number. We have lots of data points. So this is our system of equations, and if you look at this system, we can actually factor this out to be a matrix equation system, just like we've done before. And I'm just going to go ahead and do that here and come back. Well, I changed my mind. I think I should do it on video so that we see. So this is a naught, but and this is x1, but this is actually x1 to the 0th power, and this is x1 to the 1th power. This is x2 to the 0th power. This is x2 to the 1th power. x3 to the 0, x3 to the 1. You can see I didn't change anything, but this is going to be important because we're going to generalize it out to the general system. And so then we're going to have, let me just write this out then, x1 to the 0, x2 to the 0, dot 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 xn to the 0, and then we're going to have x1 to the 1, x2 to the 1, dot 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 xn to the 1. Okay, so there's our matrix here. And then we're going to have only just a naught and a1, a naught and a1, and that is equal to y all the way down, y1, y2, all the way down to yn. Now, I've shown you this because there's going to be a really nifty trick that we can do. But I don't want to only show you that. I also want to write out these equations in summation notation. So this same system of equations, and if we had more coefficients and higher powers, they would just go, higher powers would go in the next columns, more coefficients would go in the next columns, you see, and so forth. So this system of equations can also be written out in the following form. Alright, so I changed my mind. I want to write out the equation for the error, and I want to write out the equation for the equation for the error. And so the equation for the error, EI equals, and we already saw up here, EI equals, well, we know what EI equals, but let's sum up all the errors. So in general, then we're going to have the sum, then, erase. So we have the errors, but what we like to do is sum up the errors, and they call this SR in the book. So the sum of all the errors. This is actually the same thing we did before when we summed up all the errors when you saw the variance before. So summing up all the errors, the sum of the errors. So that's the sum from I equals 1 to n. So the sum of the square root of the errors, EI squared. Okay, that's the squared errors, and that's actually just going to equal to the sum from I equals 1 to n of EI. Okay, so we can rewrite EI, right? Because EI is just YI minus. Now we have to put in our equation, right? And our equation is A naught A naught minus, well, our equation is A naught plus X, A1X I, Y equals. Okay, so that's Y, and so that's what our equation is going to be. So Y hat, let's call that Y hat, because because the actual y may not lie on the line, so we'll call that line y hat. So minus a1 x I. Okay, and then let's square it. Okay, so this is the sum of the squares of the errors. The sum of the squares of the errors. Now, I didn't mention this before, but we can fit any line. Okay, we can fit any line we want to this. I mean, we could draw a line there, we could draw a line here, we could draw a line there. We could draw like tons of different lines here. And so then the question is, which line do we pick? Like, how do we know how to constrain it? Because if we already know it's not going to go through the points, we could draw a really bad line like way far away, or we could draw a pretty good one right through. And so which line should we draw? Well, so that's where the error equation helps us out. The error equation says, well, why don't you draw the line that minimizes? So we want to minimize the sum of the squares of the residuals. Okay, so well, that is equal, but let's minimize the sum I equals 1 to n of epsilon over ei squared. We want to minimize that, right? Whatever line, there are an infinite number of lines that we could fit, and those lines then are going to be a different alpha naught and a different alpha 1. And so we want the one that has the least error, and we can actually write this out. This is actually really interesting. So let me get a nice little axis here, and we can write this out in a couple of different dimensions. And so we're going to have, so I'm going to put on the y-axis, so this axis is going to be our, so the y-axis on this graph is going to be the sum of ei squared equals 1 to n. So that's going to be the y-axis here. And then we're going to need two more axes. Okay, we're going to need the a naught axis, and we're going to, well, I can do the a naught axis and the a1 axis. Okay, and then we're going to have, now this is a quadratic. This is the error squared. And the whole reason that we use the error squared is because it turns out to be a nice function here. Look at this. This is a quadratic, so this is a well-behaved function, and it's in two dimensions here. So it's not just, you know, it's a nice quadratic thing here. All right, and this probably doesn't go down to 0. Right? But this is the error. And so depending on what our a naught and our a1 is, there's going to, with certain a naught and a1, we're going to increase our error. As we decrease a1 and a naught to the right values, when we get just the right values, we're going to minimize the error. That's going to be the point that lies right down at the bottom of this bowl. Okay. And so because we skipped the chapter on optimization, we're going to have to remember how we minimize a function. So if you'll remember, that's when the derivative is equal to 0. So the minimum, min is when f of x equals 0. Or f prime of x. So we know that if it's at a minimum, the derivative at that point is going to be 0. Now, it doesn't mean it's a global minimum. It could just be a local minimum, but it's at a minimum when f prime of x is equal to 0. Well, so instead of just doing actually f prime of x, we've got a function of two variables, and so we're going to have to differentiate this equation with respect to a naught and with respect to a1 and set that equal to 0. So we can go ahead and do that here. So that means we're taking, I'm going to switch colors, so that means that we're taking the partial derivative of SR, because we want to minimize the sum of the residuals, with partial derivative of SR with respect to a naught, and we're going to set that equal to 0, and that is going to be equal to minus 2 times the sum from and it's I equals 1 to n, so you just remember that. yi minus a naught minus a1 x1. Okay, so all we've done here is really simple. We had this it should be an a naught. Oh no, it's with respect to a naught. Okay, that makes sense. So we had this squared here, right? We had this squared here, but we erased the squared because we had to bring, when we took the derivative with respect to a naught, we had to bring the 2 out front. So we brought the 2 out front here. We bring the 2 out front here. It'll be there eventually. So we bring the 2 out front here, and then we have to take the derivative, multiply that by the derivative dA naught, right? And that's minus 1. And so then so the first equation is minus 2 times this sum. Okay, so the second equation then is the partial of SR with respect to A1. Well, and set that equal to 0. So that's going to equal, well, our original equation, so let's just write it out. The sum yi minus a naught minus a1 x1, and so we had it squared right here, right? So the first thing, we take the 2 out front, so that'll just be hanging out here, and I'm going to move it over here a little bit more. So that 2 will be hanging out here, and then we're going to have to take the derivative of the inside, so with respect to a1, so that's going to be, this part's going to be 0, and this part's going to be 0, and this part's going to be 0. Oh, and of course that power goes away. And let's see, this part here, let's see, we're going to have the derivative of a1 x1 with respect to a1, and so that's just going to be minus x1, right? So I'll just put the x1 here. Well, yeah, the x1 here. And I can put the a1. No, there's no a1. I can put the minus out here. And we're going to have to probably put this whole thing in brackets because it's not x1. It's xi. Sorry, I didn't mean x1. It's xi because we're summing over I. If it were x1, there would be nothing to sum over. Sum xi. Okay, so those are the equations that we want to minimize. So we minimize. So when these are true, that's it. We just solve these 2 simultaneous equations. We've got our answer. All right, so when we solve those equations out, here we go. When we solve those equations out, this is what we get. So we have our a1. And I just don't think it's worthwhile to show all that math. We have a1 equals this, a naught equals this. Okay, that's all there is to it. A1 equals n sum xi yi minus sum xi yi all over n sum xi squared. So you square them before you sum them, and then minus the sum. So you sum them before you square them. Here you square them before you sum them. And you multiply by n here and by n here. So that's all there is to it. And then a naught is equal to y bar minus a1 x bar. So those are the equations, and that's how you come up with them. Now, I want to show you the other way that we can come up with them. Okay, now this is really good the way I showed you because we're minimizing the sum of the squared errors. So these errors, the SR is equal to the sum of the errors squared, and by taking the partial derivatives, like I showed you, we're minimizing the sum of the squared errors, which is basically finding the minimum of this function. Well, the other thing that we could do is solve this system of equations. Now, this system of equations looks a little bit funny because we have this long skinny, so we don't have the same number of equations as unknowns. We have more equations than unknowns. And so if we call this a matrix A, let's say, and this is the vector x and this is the vector b, we've got this long skinny A and this short x and then this long b. And so the trick that we can pull here, and if we do it by both sides, it's fair game, right? And so we can multiply both sides by A transpose, and so that then on this side is going to be A transpose, right? So that's going to be, you know, x naught, or x1 to the 0, dot dot dot, xn to the 0, and then x 1 to the 1, dot dot dot, x n to the 1. So you see the point here. So we're going to have all the x's, and if we left multiply them over here, we've got to left multiply them over here. So we put the A transpose here too, and then here too. And this is really interesting because what is the result of this matrix multiplication? Well, the result of this multiplication is actually a 2 by 2 matrix. This matrix here multiplied by this matrix here, because this is a 2. Remembering our rules for matrix multiplication, this is a 2 by n, and this is an n by 2. Okay, so the product of that, so the inner dimensions match, so we can multiply, that's good. And the product of that then is going to be 2 by 2. Perfect, just what we want. And then the product of this is going to be a 2 by n, and then that's our A. And then the other one is going to be n by 1. And so our answer then is going to be 2 by 1. So we're going to reduce this system. In this way, we reduce this system to a set of equations with only 2 equations and 2 unknowns. And the idea is that we're compressing all of the information that's in these x's. We're compressing it all together into one 2 by 2 matrix A, and we're compressing it all in, and all the B information in. We're combining it with this X information, and we're compressing it into this very short 2 by 1 B, and then we're just solving that system of equations for our A naught and our A1. And it turns out, and this is actually sort of similar if you think of it, the X times this. So this is similar to squaring things, and so this actually turns out to be the same set of equations. So if you solve this matrix set of equations, okay, and then if you solve these equations here that we came up with, it turns out that they're actually the exact same set of equations, and they have this wonderful name. They're called the normal equations. So that is all on this unit, and so we have, well, it's not quite all. That's basically linear regression. That's all it takes to find our coefficients. However, just as we saw in the case where we did the constant, we not only have our line here, but we also have an idea of what the spread around that line is, and so that's where this comes in. And so I've shown you already how to compute this SYX here, but that's probably not the most common thing that you've seen. The most common thing that you've probably seen is this variable called r squared. So before we finish, we probably ought to describe how we come up with r squared. Well, it just so happens that r squared is equal to this st minus sr all over st, and st again is equal to the square root of, excuse me, I'm confused. It's equal to the total sum of squares, so that's equal to the sum from I equals 1 to n, of course, like we always have here, of yi minus y bar squared. So this is just the sum of the squares of the errors. This is what we used in the numerator of our variance term. Okay, so that's ST, and of course SR, just as you saw there, SR equals the sum of yi minus A naught, excuse me, A naught minus A1 x1 or xi, there we go, squared. And really, maybe we should really think about this as the sum from I equals 1 to n of yi minus A naught squared. Okay, so I mean, even though I mean, to be clear, this may not be the same A naught, but it would have been the A naught if we had only estimated one instead of two parameters. So just to be clear about that. So in favor of this notation, I'll erase it, but it's a good insight for you to have about what's going on. And so that's r squared. And so you've seen r squared before, probably when you fit a line to 2 points. If you've ever done that before, which you may have done before, we come up with this statistic r squared, and now you know what it is. And so that is that wraps up linear regression.